So in this problem, we need to show the derivative of y with respect to x is given by the following expression whenever we are provided with this implicit function. So let's begin. We'll start off with this particular implicit function, which is square root of 1 minus x raised to the power of 6 plus square root of 1 minus y raised to the power of 6 equals to a times x cubed minus y cubed. Now, we will not take the derivative on both sides with respect to x straight away. What we'll do, we'll make a trigonometric substitution first. We'll try to simplify this given expression. So what we'll do, we'll consider x cubed to be equals to sine theta, and we'll consider y cubed to be equals to sine phi. Now let's make this substitution into equation number 1. So we have square root of 1 minus sine squared theta plus square root of 1 minus sine squared phi. So this will be equals to a times x cubed will be sine theta minus sine phi. Now this is an identity. We know that sine squared theta plus cosine squared theta equals to 1. So that means square root of 1 minus sine squared theta is simply cosine of theta. Similarly, square root of 1 minus sine squared phi will be cosine of phi. So this will be equals to a multiplied to sine of theta minus sine of phi. Right. Now we will combine cosine theta plus cosine of phi. So we are going to use the identity here of trigonometry. That means if we have cosine of A, we add it to cosine of B. So that's given by 2 times cosine of A plus B over 2 multiplied to cosine of A minus B divided by 2. And if we have sine of A minus sine of B, so that's given by 2 times cosine of A plus B divided by 2 multiplied to sine of A minus B divided by 2. So let's use this trigonometric, two of the trigonometric identities. So we'll combine cosine theta to cosine phi to get 2 times cosine of theta plus phi divided by 2 multiplied to cosine of theta minus phi divided by 2. And on the right hand side we have sine theta minus sine phi, so this will get combined to give us 2 times cosine of theta minus phi divided by theta plus phi divided by 2 multiplied to sine theta minus phi divided by 2. So we have a reduced form given by cosine of theta minus phi divided by 2 equals to a times sine theta minus phi divided by 2. Or we can simply express it as sine of theta minus phi divided by 2 whole divided by cosine of theta minus phi divided by 2. So this ratio will be equals to 1 over a. Now we know that sine over cosine, this ratio is defined as the tangent function. So here we have tangent of theta minus phi over 2. This will be equals to 1 over a. Now we'll take the inverse tangent function on both sides, which will give us theta minus phi divided by 2 equals to tangent inverse of 1 over a. Multiplying 2 will on both sides will get theta minus phi equals to 2 times tangent inverse of 1 over a. So we started out by considering x cubed to be equals to sine theta. So this would mean that theta must be equals to sine inverse of x cubed, and we have considered y cubed to be equals to sine phi, which would mean that phi must be equals to sine inverse of y cubed. So we'll replace this value here, and this gives us sine inverse of x cubed minus sine inverse of y cubed. So this will be equals to 2 times tangent inverse of 1 over a. So this particular equation, this inverse trig equation, is actually the same as equation number 1 or when we make the transformation x cubed with sine theta and y cubed with sine phi. But we have gone through all this process because taking the derivative of this particular inverse trig function will be way easier. Now let's take the derivative of each terms with respect to x. So we have derivative with respect to x of sine inverse of x cubed minus derivative with respect to x of sine inverse of y cubed. So this will be equals to derivative with respect to x of 2 times tangent inverse of 1 over a. Here we are going to use the fact that whenever we have derivative with respect to u of the inverse sine function, that's given by 1 over square root of 1 minus u squared. So applying this, we will get 1 divided by square root of 1 minus, so we have x cube here, so we'll write it as x cube squared, which will be x raised to the power of 6. But we'll also have to use the chain rule, so we'll multiply it to derivative with respect to x of x cube minus, similarly we have 1 divided by square root of 1 minus y raised to the power of 6. So we'll have derivative to it multiplied to it derivative with respect to x of y cube, which will be equals to 0 because a is a constant, so 2 times tangent inverse of 1 over a is going to be a constant and its derivative will be 0. Now we have derivative of x cubed, so that's simply 3x squared. So we have 3x squared divided by 1 minus x raised to the power of 6 minus derivative of y cubed will be 3y squared divided by square root of 1 minus y raised to the power of 6. But since we are taking the derivative of y with respect to x, we'll have to use the chain rule and multiply it to derivative of y with respect to x. So this will be equals to 0. So that means we now have 3y squared divided by square root of 1 minus y raised to the power of 6 times derivative of y with respect to x will be equals to 3x squared divided by square root of 1 minus x raised to the power of 6. So we can factor out 3 from both sides and rewrite our equation as dy over dx equals to x squared multiplied to 1 minus y raised to the power of 6 divided by y squared times square root of 1 minus x raised to the power of 6. So this is what we were asked to prove, and hence we have successfully showed that as well.